This is the second part of our discussion on linear transformations. So in the previous part, we saw what are linear transformations and what is the beautiful geometry related to those linear transformations. So a linear transformation is a complex valued function of the form az plus b, where a and b are complex numbers. Now we also saw in the previous part that a linear transformation is a composition of translation, rotation, and magnification. Now in this part, we are going to construct some examples of linear transformation with given data. For example, if it is given that construct a linear transformation that translates by this vector and rotates by this angle and magnifies by this factor. We will also see some examples where we try to find the image of a given set in the z plane under a linear transformation in the w plane. Now let's begin with our first example where we are given an ellipse in the plane. So an ellipse is a shape of the form this. Now in particular, we are given an ellipse with horizontal major axis of 4 units. So if I take the center of this ellipse to be the origin, then this length is given to be 4 units. So if this is 2, then this is minus 2. And vertical minor axis of 2 units. So in other words, this length is 2 units. So if this is iota, then this is minus iota. Now we have the following parametric representation of this ellipse, which is 2 cosine t plus iota sine t. Now what does it mean that this is the parametric representation? So it means that when t is equal to 0, we are at this point, and when we increase the values of t, then we are moving along this ellipse and we are moving in this direction, and when t is equal to 2 pi, we are arriving at the same point, and that's how this parameterization represents this ellipse. Okay, so there is a direction of motion along this ellipse. Now we want to construct a linear transformation that rotate the ellipse by an angle of pi by 3 radians first, and secondly, it also shift the center of the ellipse 3 units to the right and 1 unit up. So what does it mean by rotation by an angle of pi by 3? So in other words, we want a linear transformation that rotate the whole ellipse by pi by 3 angle. Okay, so this is the angle pi by 3. And it shifts the center of ellipse 3 units to the right and 1 unit up. So in other words, what we are saying is it translates the ellipse. It translates the ellipse by this vector b. Okay, so which is 3 units to the right. In other words, we are moving in the along the real axis, and 1 unit up. In other words, we are moving 1 unit in the direction of imaginary axis. Okay, so we want a linear transformation that translates by this complex number. Okay, now let's see how to construct this linear transformation. Now let's say our linear transformation is r of t. Now in the first step, we want a rotation by pi by 3 angle. So in other words, we will multiply with e raised to power iota pi by 3, and we will multiply it with s of t. And we also want a 3 unit to the right and 1 unit up translation. In other words, 3 unit to the right along real axis and 1 unit up, in other words, along imaginary axis. So we have the following linear transformation, which is e raised to power iota pi by 3 s of t plus 3 plus iota. Now we can further simplify this linear transformation by using the Euler formula. E raised to power iota pi by 3 is basically cosine pi by 3 plus iota sine pi by 3. And we can also write down the value of s of t, which is 2 cosine t plus iota sine t. Now we can multiply these two expressions and we will get the following. And we can further simplify this expression in the following form. Now this is r of t. Or we can write it down, instead of using iota, we can write it down in the coordinate form as well. Now this is the linear transformation which rotates this ellipse by an angle of pi by 3, and it also translates it by this complex number 3 plus iota. Now let's consider our next example where we are given a linear transformation, and the question is find the image of the disk under this transformation. Now what is this disk? Now we can see that there is a strict inequality here. There is no equality, so this is an open disk. And what is the center of this disk? The center of this disk is 1, and the radius of this open disk is 1. So this is 1, let's say this is 2. So basically this is the following open disk. So the boundary is dotted because the boundary is not included, but inside of this disk is included. Now we want to see what is the image of this open disk in the W plane. Okay, so this is the W plane. Now what is f of this disk? Okay, so let's call this disk to be A. Now what is f of A in W plane? Now let's see how to answer this question. Now in the first step, we construct the inverse of this linear transformation. We know that we have observed in our previous discussion that a linear transformation is always a one-to-one and onto on the entire complex plane. So that's why we can construct its inverse. So to construct its inverse, we write it down as 3 plus 4 iota z minus 2 plus iota. So from here we can find the value of z in the following form. So z is equal to w plus 2 minus iota divided by 3 plus 4 iota. Okay, so in other words, we have the following inverse of this linear transformation. Now this inverse is going to help us in finding the image of this disk in the W plane. Now let's see how. So an element W belongs to the image of this disk if and only if the inverse of that W belongs to the set A. The set A is basically this disk. Okay, so this is the disk, and let's say we don't know the image of this A yet, but let's say this is f of A. Now an element W of this W plane, so let's say this is the element, so this belongs to f of A if and only if the inverse image, okay, so if we apply inverse function on W, then this must belong to the set A, which is this open disk. And if W does not belong to this f of A, if let's say this is some other W, let's say W prime, then this definitely does not belong to the set A because it is not in the image. So that's why we can say that all those W's such that f inverse W belongs to A are the elements of the image of this disk. Okay, so let's apply the definition of f inverse. So what we get, W plus 2 minus iota over 3 plus 4 iota must belong to A. Now we know a very well defined description of the set. So an element Z belongs to this set A if Z minus 1 mod is strictly less than 1. And we are here claiming that this element belongs to A. So what should happen? So W plus 2 minus iota divided by 3 plus 4 iota minus 1 should be less than 1. Now we can also multiply, to simplify this thing, we can multiply this expression by 3 plus 4 iota, and what do we get? So we get this expression. Okay, so here we just multiply both sides of inequality by the mod of 3 plus 4 iota. And simplifying this, we get the following form. So of course we can calculate the modulus or the absolute value of 3 plus 4 iota to be 5, and multiplying 3 plus 4 iota, so this will cancel out and we get the following expression. Now multiplying them and simplifying, we get the following expression. So there is no mod here. Okay. And further simplifying, we get the following expression, and once again there is no mod here. Okay. So we have the following answer. So what is the image of this disk A then? Okay, so it is set in the W plane. Now we can see that this is once again an open disk with center 1 plus 5 iota. Okay, so we can write it down in the following form: W minus 1 plus 5 iota mod less than 5. And this is the center, and this is the radius. So we have to choose our scales very small: 1, 2, 3, 4, 5. So what is the center? So the center is 1 plus 5 iota. So 1, 2, 3, 4, 5. So this is the center of our disk. And what is the radius? The radius is 5. So in other words, it will be something like that. Okay, so it's going to be. So this is the image f of A. And of course, we know what is A. So A is basically a disk with center 1, open disk with center 1 and radius 1. So this is the image under this linear transformation of the set A. Okay. So in this example, we use the inverse of this linear transformation. Now let's consider another example where we want to find the image of this half plane under this linear transformation. Now what is this half plane? So it is set of all complex numbers such that the imaginary part of that complex number is greater than 1. Now let's see geometrically what is this half plane. So this is the real axis and this is the imaginary axis. Now we want to find all complex numbers in the z plane such that the imaginary part of the complex number is strictly greater than 1. Now if this is 1, in fact this is iota, then we want to find all complex numbers such that the imaginary part is strictly greater than 1. So this is the imaginary axis. So in other words, we want to find all complex numbers which are above this thing. And since it is strictly greater than 1, so the points on this line will not be included. And as we can see that this is half plane, not a full plane. So that's why imaginary part of z strictly greater than 1 is a half plane. Now what do we want to know? So we want to know that what is the image of this half plane under this linear transformation f of z. Now let's see how to find the answer. Now in the first step, we will find the real and imaginary parts of this complex valued function. So in other words, if we assume that z is equal to x plus iota y, then we want to find what is f of z, 3 plus 4 iota multiplied by x plus iota y minus 2 plus iota. And we can further simplify it and we get the following answer. So here the value of u is equal to 3x minus 4y minus 2, and the imaginary part is 3y plus 4x plus 1. Now once again, if we want to calculate the image under this linear transformation of this set, okay, so let's say this set is A. Okay, now the point is we have only one information, okay, and that information is, okay, so let's say this is the set A, which is the half plane. We want to know once again what is, so we don't know the answer yet, so we want to know what is this f of A. So once again, what do we know about this f of A? So we know that if there is some element uv here, and when we calculate the inverse image, then the imaginary part of that inverse image, okay, so f inverse of z, and if we calculate the imaginary part of this f inverse z, then it should be strictly greater than 1. So how to apply this condition? So to apply this condition, we find the value of y from this expression of v, and we impose the condition that y is greater than 1, because y is basically the imaginary part. So in other words, in the first step, we calculate the value of y from here. So y is equal to v minus 4x minus 1 divided by 3. And then using this condition, because if this u and v belongs to f of a, the image of this half plane, then the imaginary part or y should be strictly greater than 1. So in other words, we have the following inequality. So this is the value of y, it should be greater than 1. So this implies v minus 4x minus 1 divided by 3 should be greater than 1. And from here, we have v minus 4x minus 1 strictly greater than 3. And from here, we have this final answer, v is strictly greater than 4 plus 4x. Now, once again, remember, what do we want to calculate? We want to calculate an expression, inequality or equations in terms of u and v that defines the image of this half plane in the w plane. Now, that's not what we want here, because this inequality involves v as well as x. But we want an inequality which involves only u as well as v. Now, to solve this problem, we try to find the value of x in terms of u and v and then use that value here. So for that, we consider the expression of u and find the value of x from here. Okay, so this is the expression u, and from here we can easily find the value of x. Now, what is the problem in this expression? So the problem in this expression is this x involves y here. Since we want to replace the value of x so that we get expression in terms of u and v, so that's why we want to replace this y and use the value of y in terms of u and v, and of course x, because then we can collect x. And from here we can simplify it and we get the following value of x, which only involves u and v. And we can use this value of x in the expression v strictly greater than 4 plus 4x, and using this value of x we get an answer which only involves u and v. So here this inequality defines the image of this half plane in the w plane. Now, what does this inequality represent? Now, this inequality can be written in the following form. So v minus 4 over 3u minus 68 by 3 strictly greater than 0. Okay. Now, this u and v, so if we just construct this function, so v minus 4 by 3u minus 68 by 3 equal to 0, then this is basically a line in the uv plane. Okay, so in the w plane, so this is a line, and we can see that the intercept is minus 68 by 3 and the slope is minus 4 by 3, so it will be a line of the following form. Okay, so this is basically minus 68 by 3. Now this line represents the values when u and v satisfy this equation. But what do we want to get? We want to get the values of u and v that satisfy this inequality. Okay, so in other words, we want that the value of v is strictly greater than this expression, and this line represents those values when the value of v is equal to 4u plus 68 by 3. So in other words, our answer is going to be this part. So these are all the values, these are all the points where v is strictly greater than 4u plus 68 by 3. So this is the geometry of our image. So similarly, we can calculate other examples where we are given a linear transformation and a set in the z plane, and we can construct its image in the w plane. So far, we discussed what are linear transformations, what are the geometrical interpretations of these linear transformations, and in this part, we saw how to construct different linear transformations using given information. For example, if the given information is the translation or this linear transformation should rotate and should translate this much by this much complex number, then we constructed that linear transformation. So we also observed that how to construct the images in the W plane.